X-ray tube. Part 1. This tutorial is presented by Arindam Sarkar. This part of the tutorial describes the different components of the X-ray tube, their structure and functions. Introduction. This illustration depicts the simplified form of an X-ray tube showing its major components. The X-ray tube provides an environment for X-ray production via Bremsstrahlung and characteristic radiation. This requires electrons with high kinetic energy to hit a metal target. To accomplish this task, the X-ray tube contains an electron source from a heated tungsten filament with a focusing cup serving as the negative electrode or cathode, a target serving as the positive electrode or anode, and a tube envelope to maintain an interior vacuum. This entire assembly is accommodated in a protective tube housing. Major components of the X-ray tube are the cathode, anode, glass or metal envelope, and tube housing. The filament is heated by a current that controls the thermionic emission of electrons, which in turn determines the number of electrons flowing from cathode to anode. This current is called the tube or anode current. The tube current ranges from less than 10 mA in fluoroscopy and 100 to greater than 1000 mA in a single exposure. The potential difference applied between the cathode and anode that accelerates the electrons emitted from cathode controls both X-ray energy and intensity. The applied voltage between anode and cathode ranges from 40 to 150 kV for general diagnostic radiology and 25 to 40 kV in mammography. Two main external power supplies that operate the X-ray tube are filament current supply and tube voltage supply. Cathode. The cathode is the negative electrode in the X-ray tube and is located at one end of the tube. It is responsible for emitting electrons, which are then accelerated towards the anode to create X-rays. The cathode consists of a filament and a focusing cup. The filament is made of tungsten wire of approximately 0.1 to 0.3 mm diameter, which is wound in a form of helix and is electrically connected to the filament circuit, which provides a voltage of approximately 10 volt and a variable current up to 7000 mA, that is 7 ampere. The filament is electrically heated to a high temperature, usually around 2200 degrees Celsius, by passing an electrical current through it. This causes the filament to emit electrons through a process called thermionic emission. Most X-ray tubes for diagnostic imaging have two filaments, one large and one small. The focal size of the X-ray tube is dependent on the size of the filament. The dimensions of the large and small filament can vary depending on the specific make and model of the tube. However, here are some typical dimensions of the filament. For the large focus, typically ranges from 0.8 mm to 1.2 mm in diameter and 7 mm to 10 mm in length. For the small focus, typically ranges from 0.2 mm to 0.6 mm in diameter and 1 mm to 3 mm in length. The small focus is used for higher resolution imaging and is ideal for imaging small structures where lower amount of X-ray energy is required, typically below 300 mA. The large focus, on the other hand, is used for larger structures or when a higher amount of X-ray energy is required. Each filament is positioned in a slot machined into the focusing cup, with one end directly connected to the focusing cup, and the other end electrically insulated from the cup by a ceramic insert. Only one filament is energized for an imaging examination. On many X-ray systems, the small or the large filament can be manually selected or automatically selected by the X-ray generator depending on the technique factors, that is, kV and mAs. Tungsten is the most commonly used material for the filament in X-ray tubes due to its high melting point and excellent resistance to thermal and mechanical stress that can withstand positive ion bombardment. The melting point of tungsten is around 3400 degrees Celsius, which allows it to withstand the high temperatures generated during the operation of the X-ray tube. Additionally, tungsten has a low vapor pressure, which reduces the likelihood of filament evaporation and deposition on the glass envelope of the X-ray tube, which could result in arcing and reduced tube life. The low vapor pressure also allows for a stable electron emission over time, which is important for consistent tube performance. Tungsten is also readily available, relatively low cost, and can be easily drawn into very thin wire and shaped into helical form because of its greater mechanical strength. Further, to minimize the evaporation of tungsten from the hot surface, the filament temperature is kept at a lower level except during exposure when it is raised to operational levels for thermionic emission of electrons. Without the focusing cup, the negatively charged electrons emitted from the filament would be electrostatically repelled among themselves in all directions, resulting in a broad electron beam that would hit the anode in a diffuse pattern rather than a focused spot. This would reduce the efficiency of the X-ray production and degrade the image quality. The focusing cup, which is located around the filament, forms a part of the negatively charged electrode and helps to focus the emitted electrons towards the anode. The biasing electrode is also negatively charged and helps to shape and direct the electron beam current towards the anode, allowing for a more concentrated and efficient X-ray production. In most X-ray tubes, the focusing cup is maintained at the same potential difference as the filament relative to the anode. This is illustrated as an unbiased circuit to the left. At the edge of the slot, an electric field exists that repels and shapes the cloud of emitted electrons from the filament surface. As a large voltage is applied between the cathode and anode in the correct polarity, electrons are accelerated into a tight distribution and travel to the anode, striking a small area called the focal spot. The electron distribution in a typical bimodal distribution of the current density can be seen in a pinhole image of the focus. The illustration in the middle depicts a biased focusing cup where the focusing cup is isolated from the filament and a negative bias voltage, approximately -100 volt, is applied. This reduces electron distribution further to a monomodal distribution by increasing the repelling electric fields surrounding the filament and modifying the electron trajectories. With an increasing negative bias voltage at the focusing cup, the focus size will decrease and finally the electron current will be pinched off. This pinch-off effect is sometimes used to electronically control the focus size or for a fast switching of the anode current in grid-controlled tubes when short radiation pulses are required, as in pulsed fluoroscopy. This is illustrated by the grid-pulsed focusing cup on the right. The focal spot dimensions are determined by the length of the filament in one direction and the width of electron distribution in the perpendicular direction. The large focal spot is used with an area large enough to permit a sufficiently large tube current and short exposure time. For magnification studies, A small focal spot is necessary to limit geometric blurring and achieve adequate spatial resolution. We will cover more on focal spot later when we discuss about anode. Space charge and space charge effect. As a result of thermionic emission, a small cloud of negatively charged electrons is formed in the vicinity of filament. This cloud of electron is called space charge. This cloud of negative charges opposes the release of additional electrons from the filament. This tendency of space charge to limit the emission of more electrons from the filament is called space charge effect. The number of electrons in space charge remain almost constant. At low tube voltages and high filament current, the space charge effect happens because electrons are released from the filament more rapidly than they are pulled toward the target. At higher tube voltages, space charge effect is overcome by applied potential difference. Filament current and tube current. Two electrical currents flow in an X-ray tube: the filament current and the tube current. The X-ray tube current is actually controlled by changing the filament current. The filament current flows when a low voltage, typically between 3 to 15 volt depending on the specific tube design, is applied across the filament by an external filament power supply circuit. The electrical resistance to the filament current heats the filament, and as a result of this heating, the process of thermionic emission occurs, which releases electrons from the filament surface at a rate determined by the filament current and corresponding filament temperature. However, the tube current flows only when the tube voltage is applied between the cathode and anode, allowing the electrons released from the filament due to thermionic emission to move from the cathode to the anode. The tube current is dependent on the numbers of electrons released by thermionic emission that is adjusted by the filament current and filament temperature. The illustration on the left for filament characteristics shows the plot of tube current against filament current at different tube voltages. Here, the tube current starts flowing when filament current is greater than 3.5 ampere. Below this filament current, the thermionic emission of electron is negligible. From the shape of the curves, it is obvious that the filament current and X-ray tube current are nonlinearly related. At higher filament current settings, a small changes in the filament current produces relatively larger changes in tube current than at lower filament current settings. For example, at 80 kV, if the filament current is raised from 5 ampere to 5.1 ampere, the tube current increases by 0.12 ampere or 120 mA. Whereas, at 80 kV, if the filament current is raised from 4 ampere to 4.1 ampere, the tube current increases by 0.03 ampere or 30 mA. This is because the amount of thermionic emission increases rapidly as the filament current is raised. Also, higher tube voltages produce slightly higher tube current for the same filament current. A filament current of 5 ampere at a tube voltage of 80 kV produces a tube current of about 800 mA, whereas the same filament current at 120 kV produces a tube current of about 1100 mA. This is because, at this applied tube voltage, the rate at which electrons are drawn towards the anode is less than the rate at which electrons are released from the filament. This condition implies that the X-ray tube is operating below the saturation voltage at this filament current. The illustration on the right shows how the tube current varies with change in kV at different filament current settings. The darker shaded portion to the left represents the unsaturated condition of the X-ray tube. At a given filament current, tube current reaches a maximum level called saturation current. The lighter shaded portion to the right represents the saturated condition of the X-ray tube. Above the saturation point, the tube current is limited by the rate at which electrons are released from the filament. The tube current is said to be filament emission limited. Above the saturation point, the tube current remains almost constant with increasing tube voltage. Here, the tube current can be increased only by raising the filament current in order to increase the rate of electron emission. At a low filament current, a saturation point is reached at a lower tube voltage. Referring back to the illustration on the left, please note that at high filament currents and lower tube voltages, 40 kVp or lower, the space charge limits the tube current, and hence the X-ray tube is said to be space charge limited. X-ray tube envelope. The tube envelope maintains the required vacuum in the X-ray tube. The X-ray tube envelope increases X-ray production efficiency. Failing vacuum due to leakage or degassing of the materials causes increased ionization of the gas molecules, which slows down the electron acceleration. Further, a current of positive ions flowing back could impair or destroy the cathode filament. The X-ray tube envelope encases the two electrodes, the cathode or negative electrode and the anode or positive electrode. The envelope is commonly made of Pyrex glass, but high-performance tubes increasingly have combination of glass and metal or ceramic and metal. The X-ray beam exits the tube through a window in the envelope. To reduce absorption, the thickness of the glass is reduced in this X-ray window area. The area measures approximately 5 square centimeter. Dimension of the X-ray tube envelope varies with power rating. The typical diameter of the X-ray tube envelope is around 10 to 20 centimeters, and the length of the tube can range from 20 to 70 centimeters. The exact dimensions of the envelope may also depend on the focal spot size, heat capacity, and cooling requirements of the specific X-ray tube. Glass versus metal envelope. Glass envelope. Pyrex glass, also known as borosilicate glass, is used for the tube envelope. Pyrex glass has low thermal expansion and less likely to crack with heat. It is a good insulator and can withstand the high voltage. However, glass envelopes are subject to aging that can lead to tube failure. Tungsten vaporized from the filament gets deposited on the inner wall of the glass envelope. Due to this deposition, the glass gradually becomes bronze-colored or sunburn. This has two effects. First, filtration of the X-ray beam increases. That leads to gradual change in the quality of the X-ray beam. Second, due to the presence of metal deposit on the glass surface, the envelope itself starts acting like an electrode in between the cathode and anode and causes arcing at high peak voltages. Metal envelope. Partial or full. Metal envelopes are less likely to develop gas and filament vaporization. The metal tube is airtight and impermeable and has no suckback. These properties give superior protection to contents, keeping them fresh and uncontaminated through long periods of intermittent use. Also, they have longer life because they do not build up a metallic coating on the inside with age. Arcing problem is less due to constant electrical potential between cathode and enclosure. Grounded metal traps stray electrons, reducing off-focus radiation. Metal envelopes are used in most modern X-ray tubes with high kVp and Ma settings. Anode. An anode is an essential component of an X-ray tube that is located opposite to the cathode. It is a positively charged electrode that attracts the negatively charged electrons emitted by the cathode. The primary function of the anode is to convert the energy of the accelerated electrons into X-rays. For common radiographic applications, a high bremsstrahlung yield is mandatory, requiring materials with high atomic numbers, Z. The anode must be designed to withstand the high levels of heat generated during operation. The anode typically consists of a copper block that serves as a heat sink, with a tungstenrhenium target attached to its face. The tungstenrhenium target material is chosen because of its high melting point and thermal conductivity. The copper block that makes up the bulk of the anode serves as a heat sink, drawing heat away from the target and dissipating it into the surrounding environment. There are two types of anodes: stationary and rotating anode. Next, we will learn about the features and use of these two anode types. Stationary anode. A simple X-ray tube design has a fixed or stationary anode consisting of a tungsten insert embedded in a copper block. Copper serves a dual role. It mechanically supports the insert and efficiently conducts heat from the tungsten target. However, the small area of the focal spot on the stationary anode limits the tube current and X-ray output that can be sustained without damage from excessive temperature. Dental X-ray units and some low-output X-ray machines limited to 150 mA and mobile fluoroscopy systems use fixed anode X-ray tubes. Rotating anode. Rotating anodes are used for most diagnostic X-ray applications, mainly because of greater heat loading and higher X-ray intensity output. Unlike the stationary anode design where one spot on the target is continuously heated, this design spreads the heat over a much larger area, permitting much larger tube currents and exposure durations. The anode is a beveled tungsten disc. The illustration on the top left shows the view of the anode disc from the cathode end. The arrow indicates the direction of rotation of the anode disc. The circular path in light orange indicates the surface area of the anode that is bombarded by the electron beam. This surface area is called the focal track of the anode disc. The focal track area of the rotating anode is approximately equal to the product of the circumferential track length, 2 pi r, and the track width, delta r, where r is the radial distance from the axis of the X-ray tube to the center of the track. Thus, a rotating anode with a 5 cm focal track radius and a 1 mm track width provides a focal track with an annular area 314 times greater than that of a fixed anode with a focal spot area of 1 by 1 mm. The allowable instantaneous heat loading depends on the anode rotation speed and the focal spot area. The anode disc is mounted on a rotor assembly supported by bearings in the X-ray tube insert. The illustration on the top right shows the side view of the anode disc mounted on a rotor assembly and the stator assembly mounted outside the X-ray tube insert. This illustration in the bottom shows the cross-sectional side view of the disassembled anode disc and rotor assembly. The rotor consists of copper bars arranged around a cylindrical iron laminated core and forms the rotating part of the induction motor. A donut-shaped stator device, comprised of electromagnets, surrounds the rotor and is mounted outside of the X-ray tube insert. Alternating current is passed through the stator windings and produces a rotating magnetic field. This induces an electrical current in the rotor's copper bars, which creates an opposing magnetic field that causes it to spin. The standard rotation speed is 3000 revolutions per minute or RPM. In high-power X-ray tube, the rotor assembly is designed for higher speed of 9000 RPM. Faster rotation distributes the heat load over a greater portion of the focal track area for short exposure times. X-ray systems are designed such that the X-ray tube will not be energized if the anode is not at full speed. This is the cause for the short delay of 1 to 2 seconds when the X-ray tube exposure button is pushed. Rotor bearings are heat sensitive and are often the cause of X-ray tube failure. Bearings require special heat-insensitive, non-volatile lubricants because of the vacuum inside the X-ray tube insert and also require thermal insulation from the anode. A stem made of molybdenum, a metal with poor heat conductivity, attaches the anode to the rotor to reduce heat transfer to the rotor bearing. Most rotating anodes are cooled by infrared radiation emission, transferring heat to the X-ray tube insert and to the surrounding oil bath and tube housing. Focal spot. A focal spot is the small area on the anode of an X-ray tube where the electron beam from the cathode is focused to produce X-rays. The size of the focal spot has a significant impact on the geometric sharpness and thus image quality that results. The illustration on the left shows the object's partially shaded outer region or the penumbra formed due to the size of the focal spot. This penumbra causes blurring or a decrease in the sharpness of the subject image. The wider the penumbra, more the blurring effects of the image. The illustrations on the right, A, B and C shows different sizes of focal spot and its effect on image quality. The illustration D shows the effect of increasing the distance of the subject from the image receptor. Ideally, a focal spot would be a point, as illustrated in Figure A, eliminating geometric blurring specifically at the edges of the subject image due to absence of penumbra. However, such a focal spot is not possible and, if it were, would permit only a tiny tube current. In practice, a finite focal spot area is used with an area large enough to permit a sufficiently large tube current and short exposure time. A small focal spot, as illustrated in Figure B, causes a small blurring at the edges of the image. But a larger focal spot, as illustrated in the Figure C, allows a greater X-ray beam intensity. However, it causes a loss of spatial resolution due to increase in edge blurring. The greater is the object-to-receptor distance, the larger is the penumbra, resulting in a less sharp image, as illustrated in the Figure D. On the contrary, the greater is the source-to-object distance, the smaller is the penumbra, resulting in a sharper image. A large focal spot, which permits higher X-ray output intensity with shorter exposure time, should be used in situations where motion is expected to be a problem and geometric magnification is small, that is, the object is close to the image receptor. On the other hand, for magnification studies, a small focal spot is necessary to limit geometric blurring and achieve adequate spatial resolution. To summarize, we can say that a small focal spot produces sharper images, but the X-ray output intensity is limited. Large focal spot, on the contrary, produces X-ray output with higher intensity, but suffer from loss in image resolution. To balance the need for large X-ray intensity with that of a small focal spot size, the line focus principle is used. Line focus principle. The line focus principle is a design feature in X-ray tubes that allows for a smaller effective focal spot while maintaining a larger actual focal spot. This is achieved by angling the anode target so that it is not perpendicular to the electron beam but rather at an oblique angle. This principle is critical for improving the spatial resolution of X-ray images without sacrificing the heat loading capacity of the anode. Illustration of the line focus principle employed in X-ray anodes. Here, a cross-sectional cut through a rotating anode is shown. By beveling the edge of the anode, the electron beam, traveling in from the right in this figure, can expose a relatively large expanse of anode while the projected cross-section of the X-ray beam, traveling downward in this figure, remains relatively small. The anode angle, commonly represented by theta, is the angle between the vertical and the target surface. Anode angle in diagnostic tubes range from 6 to 22 degrees depending on their task. For general-purpose radiography, anode angle ranges from 10 to 16 degrees. Here, the height of the electron beam from the filament is represented by h and width by w. The shaded area on the anode surface indicates the focal spot. The length of the focal spot, L, where the electrons hit the anode is determined by the height h of the electron beam, which in turn is dependent on the length of the cathode filament and the anode angle theta. Larger the anode angle, greater the focal spot length. The radial dimension of the focal spot depends on the width w of the electron beam, which in turn depends on the filament coil diameter and the action of the focusing cup. The apparent or effective focal spot length appears shortened in the X-ray beam direction, determined as L sin theta. However, the radial width, h, remains unchanged. The actual focal spot area is the product of W multiplied by L, whereas the apparent or effective focal spot area is the product of W multiplied by L sin theta. That is, the apparent focal spot area is equal to product of actual focal spot area multiplied by sin theta. Decreasing the anode angle decreases the size of the effective focal spot, thus increasing the image resolution. But the heat capacity of the anode also decreases because the actual focal spot size decreases. The reduction of anode angle to achieve smaller effective focus sizes is further limited by the size of the field of view required as the X-ray beam is cut off by the anode. A further limit is given by the Heal effect. Before we discuss on the effect of anode angle over field of view and the Heal effect, we will briefly discuss about the arrangement for focal spot in rotating anode tube. The illustration shows the side view of the anode and cathode, as well as the front view of the anode. The beveled surface of the anode forms the focal track. Here, unlike the stationary anode tube, the cathode is eccentrically mounted, aligned with focal track of the anode. The anode angle, theta, is the angle of the beveled target surface with reference to the vertical or central axis. The focal spot true length, as projected down the central axis, is foreshortened according to the line focus principle to form the focal spot effective length. The focal spot effective length is dependent on both the focal spot true length and the anode angle, as already discussed. Anode angle and field coverage. Both field coverage and effective focal spot size vary with the anode angle. As the anode angle decreases, that is, approaches 0 degree, the effective focal spot becomes smaller for the same actual focal area, providing better spatial resolution of the object. However, a small anode angle limits the usable X-ray size at a given source to image receptor distance because of cutoff of the beam on the anode side. Field coverage reduces further for short focus to detector distances. A large anode angle provides good field coverage, however, geometric blurring and image degradation occur. A small anode angle limits field coverage at a given distance, however, a small effective focal spot is achieved with improved image resolution. Therefore, the optimal anode angle depends on the clinical imaging application. A small anode angle, approximately 7 to 9 degrees, is desirable for small field of view devices, such as some small fluoroscopy detectors, where field coverage is limited by the image receptor diameter, example, 23 centimeters. Larger anode angle, approximately 12 to 15 degrees, are necessary for general radiographic imaging to achieve sufficiently large field area coverage at typical focal spot to detector distances such as 100 centimeters. Focal spot distribution. The graphic representation of the focal spot shape at different locations in the radiation field is illustrated. Variation of the effective focal spot size in the image field occurs along the anode-cathode direction. Focal spot distributions are plotted as a function of projection angle in degrees from the central axis, along anode-cathode direction on the vertical axis, and perpendicular to the anode-cathode direction on the horizontal axis. The effective focal spot length varies with the position in the image plane in the anode-cathode direction. Toward the anode side of the field, the projected length of the focal spot shortens, whereas it lengthens towards the cathode side of the field. The width of the focal spot does not change appreciably with position in the image plane. Nominal focal spot size, width and length, is specified at the central ray of the beam from the focal spot to the image receptor, perpendicular to the anode-cathode axis and bisecting the plane of the image receptor. Anode heel effect. Here the X-rays produced at depth within the anode suffer some absorption losses according to the distance passed in the anode material. For X-rays emerging near the anode side of the X-ray field, the losses are higher, resulting in an inhomogeneous X-ray intensity across the beam. Absorption of X-rays at the cathode side of the X-ray field is less than at the anode side. The steep drop in intensity at the anode side results from the increased self-absorption of anode. The heel effect refers to a reduction in the X-ray beam intensity toward the anode side of the X-ray field. The dotted line on the illustration on the right shows the plot of intensity profile due to heel effect. There is an attenuation of X-ray intensity as high as 30% along cathode to anode direction. The name heel effect is derived from the shape of the intensity profile. due to Heal effect compared to the cathode side. On the anode side we get a lower X-ray intensity and harder beam due to higher self-absorption or filtration. Also we get a smaller apparent focal spot as discussed a while ago. The Heal effect becomes more pronounced with 1. Short SID, 2. Large field size, and 3. Small anode angle. Since the X-ray beam intensity is greater on the cathode side of the field, the orientation of the X-ray tube cathode over thicker parts of the patient can result in a better balance of X-ray photons transmitted through the patient and onto the image receptor. For example, the preferred orientation of the X-ray tube for a chest X-ray of a standing patient would be with the anode-cathode axis vertical and the cathode end of the X-ray tube down. However, Heal effect is often barely noticeable in radiographs, especially with higher SID. X-ray tube housing. The X-ray tube is often referred to as the insert, is installed in a housing providing the structural support required. Tube housings also provide mechanical protection against the impact on tube envelope. The space between housing and envelope is filled with transformer oil serving as electrical insulation and for heat removal from the envelope surface, which is heated by the infrared radiation from the anode. The change of the oil volume with varying temperature is taken care of by the expansion bellows. The oil carries the heat away to the housing by convection, sometimes enhanced by forced cooling with a ventilator or heat exchangers. The housing also provides radiation shielding to prevent any radiation, except the primary beam, from leaving the housing. The inside of the housing is lined with lead sheets to minimize leakage radiation. The maximum acceptable exposure due to leakage radiation is limited by regulation. Most X-ray tube housing have provision to attach added filter, usually aluminum, on the X-ray output port to absorb the unwanted soft X-rays and minimize patient dose. X-ray collimator. X-ray collimator is mounted on the tube housing to adjust the size and shape of X-ray beam radiated through the output port. The collimator contain parallel opposed lead shutters or collimator blades to adjust the size and shape of this X-ray beam. The X-ray collimator contains light field to mimic the X-ray field. The collimator light is mounted inside the collimator. Slits are used to limit the light to a specific shape and size. A radiolucent mirror positioned at a 45-degree angle to the light source allows the light to be reflected at a right angle and create a rectangular or square field of light on the patient. The light field is used to ensure that the X-ray beam is properly aligned with the image receptor, such as an X-ray film or digital detector. The light field is typically marked with a set of crosshairs that are aligned with the central axis of the X-ray beam. This helps the operator to position the patient correctly and to ensure that the X-ray beam is aimed precisely at the area of interest. With help of the light field, the operator can also adjust the collimator blades to restrict X-ray exposure to image receptor or film cassette, and to ensure that the area being irradiated by the X-ray beam is limited to the desired region, thus reducing unnecessary exposure to healthy tissues. The X-ray collimator plays an important role in reducing dose to patient and scatter radiation to image receptor. With this we conclude the first part of the tutorial on the different components of the X-ray tube, their structures and functions. In the second part we will discuss on X-ray tube rating and common faults in X-ray tube.